Kamali is preparing for examinations. She spends lot of time in studies. In common parlance, she is working hard. All this hard work may involve very little work if we go by the scientific definition of work. What did you observe? Did you notice the man who is trying to move a hard rock? He is working hard to move the rock, but it doesn't move despite all the effort. He has not done any work as there is no displacement of the rock. Do you think if there were more men, they would be able to move that rock? Let's find out the answers to these questions and understand the underlying concepts about work and energy. So, what is work? We see so many physical or mental activities in our day-to-day life, such as playing, talking with friends, climbing the stairs. They all are considered work in common parlance. However, it is defined differently in science. To understand the way we view work and define work from the point of view of science, let's consider a situation. Defining work. A boy pulls a trolley and the trolley moves through a distance. The boy has applied a force on the trolley and it is displaced from its initial position to a new position. Therefore, work is done in this situation. A closer look at this situation reveals that two conditions need to be satisfied for work to be done. A force should act on an object. The object must be displaced. If any one of the above condition does not exist, work is not considered as done. Let's first consider the case when the force is acting in the direction of displacement and figure out the relation between work and force. Note, when the force is applied in the direction of displacement, the work done in this situation is called positive. Let the constant force 1n act on an object. Let the object be displaced through a distance 1 meter in the direction of the force. Let W be the work done. We define work to be equal to the product of the force and displacement. Work done is equal to force, 1 Newton, multiplied by displacement, 1 meter. Therefore, W is equal to 1 Newton multiplied by 1 meter. Hence, W is equal to 1 Newton meter. Here the unit of work is Newton meter, which is also called joule. Thus, 1 joule is the amount of work done on an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. Force in opposite direction of displacement. Now, let's consider the case when the force is acting in the opposite direction of displacement. When the force is applied in the opposite direction of displacement, the work done in this situation is called negative. Consider a situation in which a man lifts a box from the ground with a force applied F. In the opposite direction, the force of gravity working on object. Let the object stop after a displacement S. In such a situation, the work done by the force of gravity is taken as negative and denoted by a minus sign. The work done by the force is F multiplied by minus S or minus F multiplied by S. Energy. Life is impossible without energy. The demand for energy is ever increasing because of even increasing population and increasing standard of living of people. Many of our energy sources are derived from the sun. We can also get energy from the nuclei of atoms, the interior of the earth, and the tides. Let us now understand the relationship between work and energy. So, what is energy and how is it related to work? The energy possessed by an object is thus measured in terms of its capacity of doing work. The energy of an object is its ability to do work. Energy is the cause and work is its effect. Therefore, both work and energy have the same units, which is joule. 1 joule is the energy required to do 1 joule of work. 1 kilojoule is equal to 1000 joule. Kinetic energy. Kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Let us now express the kinetic energy of an object in the form of an equation. Work done, that is W, is equal to Fs. Initial velocity u, final velocity v. Acceleration produced is equal to a. According to the relation connecting u and v of an object moving with a uniform acceleration a and the displacement s, v square minus u square is equal to 2as. S is equal to v square minus u square divided by 2a. From the chapter Force and Law of Motion, we know F is equal to m into a. Replacing F tends to ma, derivation of formulae of kinetic energy. The kinetic energy of an object moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Mass of the object is equal to m. Uniform velocity is equal to u, that is initial. Final velocity is equal to v, that is final. Distance moved is equal to s, that is displacement. Acted force is equal to F. Work done is equal to change in kinetic energy. Work done is equal to force multiplied by displacement. W is equal to F into S. Equation number 1. From third equation of motion, V square is equal to U square plus 2AS. V square minus U square divided by 2A is equal to S. Replacing value of S in equation 1. W is equal to F multiplied by V square minus U square divided by 2A. Or W is equal to M into A multiplied by V square minus U square divided by 2A. Because F is equal to MA. W is equal to 1 by 2m multiplied by V square minus U square. Kinetic energy at velocity v is calculated by taking initial velocity u is equal to 0. Ek is equal to half m multiplied by v square minus 0 square. Ek is equal to 1 by 2 mv square. Potential energy. Have you ever played with a rubber band? What happens when you stretch it? When you release the band after stretching, it regains its initial position. How does it get its original state? In the situation on previous screen, you transfer energy when you stretch a rubber band. This energy gets stored due to the work done on the object. The energy transferred to the band is called potential energy. The potential energy possessed by the object is the energy present in it by virtue of its position. Law of conservation of energy. Can we transform energy from one form to another? According to the law of conservation of energy, whenever energy gets transformed, the total energy remains unchanged. According to this law, energy can only be converted from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation remains the same. The law of conservation of energy is valid in all situations and for all kinds of transformations. Free fall. Whenever objects fall towards the earth under this force alone, we say that the objects are in free fall. Let us try to understand the meaning of free fall by performing this activity. A boy have a stone. Throw it upwards. The velocity has increased uniformly. As we see, to calculate velocity after falling 10 meters, value of g is equal to 9.8 meter per second square. S is equal to 10 meter is equal to distance of motion. Initial velocity u is equal to 0 meter per second. Using second law of motion, v square is equal to u square plus 2gs. V square is equal to 0 square plus 2 multiplied by 9.8 multiplied by 10. V square is equal to 196. V is equal to 14 meter per second. However, there is no change in direction. There is a uniform change in the magnitude of velocity. Any change in the velocity involves acceleration. When an object falls alone, an acceleration is involved. This acceleration is called acceleration due to gravitational force of the earth or acceleration due to gravity. It is denoted by g. SI unit is meter per second square. Derivation of formula of g according to second law of motion. Force is equal to mass multiplied by acceleration. Let mass of the object be m, and acceleration of falling object is g. So, force is equal to mg. This force is due to gravitational force, which equal to F is equal to g multiplied by me multiplied by m divided by re square. me is equal to mass of earth. Re is equal to radius of earth because object is approximately on the surface of earth. F is equal to mg multiplied by g multiplied by me multiplied by m divided by re square. Or g is equal to g multiplied by me divided by re square. The earth is not a perfect sphere. Equator. Radius of equator re. Radius of pole rp. The radius of earth increases from the pole to the equator. W is equal to mg. And g is equal to g multiplied by me divided by re square. Weight decreases from pole to equator. To calculate the value of g, we should put the values of g, m and r in equation. G is equal to g multiplied by m divided by r square. Namely, universal gravitational constant g is equal to 6.7 multiplied by 10 to the power minus 11 Newton meter square per kg square. Mass of the earth m is equal to 6 multiplied by 10 to the power 24 kg. Radius of the earth r is equal to 6.4 multiplied by 10 to the power 6 meter. G is equal to 6.7 multiplied by 10 to the power minus 11 multiplied by 6 multiplied by 10 to the power 24 divided by 6.4 multiplied by 10 to the power 6 whole square. G is equal to 6.7 multiplied by 6 multiplied by 10 to the power 24 minus 11 minus 12 divided by 6.4 into 6.4. G is equal to 9.8 meter per second square. Under the influence of gravitational force of the earth, let us do an activity to understand whether all objects, hollow or solid, big or small, will fall from a height at the same rate. We take a stone and paper. Observe whether both of them reach the ground simultaneously. We see that paper reaches the ground little later than the stone. This happens because of the air resistance. The air offers resistance due to friction to the motion of the falling objects. The resistance offered by air to the paper is more than the resistance offered to the stone. All equations for the uniformly accelerated motion of objects become valid with acceleration a replaced by g. V is equal to u plus gt. S is equal to ut plus half gt square. V square is equals to u square plus 2gs. U is equals to initial velocity. V is equal to final velocity. T is equal to time. Here u and v are the initial and final velocities, and s is the distance covered in time t. In applying these equations, we will take acceleration a to be positive when it is in the direction of the velocity, that is, in the direction of motion. The acceleration a will be taken as negative when it opposes the motion. Rate of doing work. Do all of us work at the same rate? Do machines consume or transfer energy at the same rate? Power is defined as the rate of doing work or the rate of transfer of energy. Power, that is P, is equal to work, that is W, divided by time, that is T, that is equal to energy, that is E, divided by time, that is T. Unit of power is equal to watt. 1 watt is equal to 1 joule per second. 1 kilowatt is equal to 1000 watts. 1 kilowatts is equal to 1000 joules per second. Commercial unit of energy. Commercial unit of energy is equal to kilowatt hour, that is kWh. What is kWh? Machine uses 1000 joule of energy every second. In 1 hour, energy consumed by machine is equal to 1 kWh. 1 kWh is equal to 1 kW multiplied by 1 hour. That is equal to 1000 watt multiplied by 3600 seconds. That is equal to 36 lakh joule. Therefore, 1 kWh is equal to 3.6 multiplied by 10 to the power 6 joule.